The Held-Karp algorithm is the solution to, or the dynamic programming solution rather, to the traveling salesman problem. Traveling salesman is like this. You're a salesman, you live in a particular town, you want to visit every town on your list, and then you want to end up back where you started, having visited each place one time. And naturally, you want the cheapest tour, so the cheapest route between all those cities, having ended up back in your hometown. We call it that hometown the depot. Held-Karp is going to build a table because it's dynamic programming. It's going to do it a little bit differently than other dynamic programs, which are a little perhaps more intuitive. What we're going to do is essentially work our way up, starting with, we're going to consider this history, S. So that's a set of vertices we visited. We're going to start by considering all the histories of size 1, then 2, then 3, then 4, all the way up till we match the size of our problem minus 1. Once we've done that, then we can simply, and by walking this index up, let's say, we're going to store basically the cheapest way, given that history of where we've been, we're going to store the cheapest route to each vertex given some history. And once we get to the end, we'll have visited everywhere, and we could, we'll know the cheapest way to get to every vertex, having visited every other vertex, and then we'll simply look for the cheapest way back home. There's just a few terms. So the main thing is going to be the C, which stands for the cost or distance. It's indexed by two things. S, which is, again, that history set of vertices. K, which is going to be a particular vertex. It's important to also notice that S is a set, so there's no ordering to the vertices in it. I'm going to write the vertices alphabetically, just for the sake of like notation or keeping track of it, or organization rather. But if you have the set of A and B, it's the same as B and A. So that's actually where this algorithm improves over the brute force solution, which is all permutations, which would be all possible tours. This is going to look at all combinations. So it's a smaller number. It's a big number, but it is smaller than all permutations. So it's an improvement. This method is really expensive, and we'll see that as I start to walk through it by hand. P is going to be this sort of breadcrumb trail. So given we're in vertex K having visited S, this is going to be essentially a map or a table entry storing where we came from previously. So we'll have a few options as we go along. When we're building up C, we'll just remember, we don't have to remember all possible routes again. We'll just remember the cheapest one and record it here. So that way we can kind of rewind one step at a time. That'll hopefully make more sense by the end. The recursive rules, I don't know if it's straightforward, but it's it's something. We have the base case here is when the history set is just the vertex we're ending in. So that means we've moved one vertex away from the start. So that's the cost of that. Well, that's just going to be the cost from going from the start, which in my example is A, to the vertex in question. The recursive case says, let's look back one step in time. So we're going to take K out of S. So it gives us a history, one step in the past, so to speak, without K involved. It's going to look for the destination X, which is going to which is the cheapest place to come from to get to K. So given our one step in the past and the costs that end up in X, add in the cost from going X to K, we're going to minimize this to find the cheapest way to get to K given our history size one step back. So that means, again, when we have this recursive setting or recursive rule, we're going to build the table out rather. Recursion is sort of top-down, dynamic programming is sort of the inverse. We're going to build bottom-up. So let's just go ahead and get started. I'm going to start with the base cases here. Base cases, I'll put in parentheses here, size is 1. So that's going to be, I'll write this down. So this means this is the cost of ending in B. Again, this is implying we've started in A. We've only visited B. So we've visited everything here, which is only B. This pen's not great. Ending in B. So this is just going to be the edge weight from A to B, which is 1. So you can see my example graph. I'll fill out the other entries here. So again, this is just, we went to C. The cost for that is 15. And then D, the cost for this is 6. Again, that's just looking up that edge weight. This is A to D, A to C, A to B. The parent entry, again, is just going to be this base case of, well, if we've ended up in B having only visited B, that implies we've come from A. So we'll just put all these down. Great. So now let's move on to, maybe I'll put this little dotted line in here. Size equal to 2. So this is our first real case. So now, as we bump up this size, this is going to be the size of our history. So we have to consider all sets of size 2, not including the start or the depot, whatever you want to call it. So we have BC, BD, and CD. Again, they're sets, so it doesn't matter. You know, I don't need to consider CB. It's the same thing as BC. For each one of these, we need to consider. We have to iterate over each vertex in the set and consider, for this history, I could end up in B or I could end up in C, right? So I need to compute all of these. So I'll B, C, ending up in B, B, C, ending up in C. This is going to be, so the trick to compute it here is, or not the trick rather, but following the recursive rule, I'm going to take B, our current vertex, out of the history. So that means we're going to look at simply C, comma C. So we're going to look at this base case plus the edge weight from going from C to B. So that means we have this value up here, 15, plus C to B, which is 6, for a total of 21. Now let's move on to this next case. I'm going to take C out of this set here, so that's going to give me this other base case. Going from here, B, and ending in C. So this base case of 1 plus B to C, 7, so it's going to be a total of 8. Because that finishes this set, we're going to move on to the next set. Again, I'll know which base case to look up because I'm going to take B out of this. That just leaves D. And there's only one, since there's only one value in that set, there's only one place to end up. Then we're going to go from D to B. So this base case up here is 6. Going from D to B is 4. That gives us a value of 10. Now we'll do the next one. Yeah, it's not an accident that my example I picked. Oh, it's from Wikipedia, so you can look at it there. They do it slightly differently. There's a side note there. The example they use, how they run through it, doesn't exactly match the pseudocode of the algorithm. So I changed this process to match the pseudocode. Anyhow, it's not a surprise that there's only 4 vertices in this graph because, well, all possible combinations of 2, 3, 4, etc. As that goes up, it gets huge. So we're going to take D out of this set, BD. So we're left with B, so that means that base case plus going from B to D. Okay, let's look up this base case. That's 1. Going from B to D is 3. Wow, okay. Now let's move on to the next. So I'm on to this next set, CD. Again, we have to iterate through each value within the set. So that is 2 different values. I take C out of this history set that only leaves D behind. That's pretty good curly braces if I don't say so. Okay, and then we go from D to C. So this base case up here is 6, plus from D to C, go over here and look, that's going to be 8 for a total value of 14. Now I'm going to put in this, C, D. I'm leaving the parent maps for this stage so later. I'm laying this out to make it easy to reference for the next stage. Anyways, I take D out of this set. I just have C. End up with C plus edge weight going from C to D. So this base case is up here. 15. And going from C to D is 12. So that's going to be 27. Oof. Not a good route. Anyways, so that's what we have here. If I pause, I have the cheapest. I've fully enumerated all the ways of. I could end up in B, given B and C. We know the cost of getting there is going to be 21. I know the cost now of ending up in C, given B and C, is going to be 8, so on and so forth. Now, at size 2, this is rather uninteresting. There's no choice to be made. We'll see size 3, it becomes more interesting. First, let's do the parent mapping. Again, this is just, since there's no choice in the matter, this is pretty straightforward. So if I end up in B, given the history of B and C, well, logically there's only one place left, right? So there's kind of nothing to this step. We'll see it becomes a little more interesting for size 3. And again, this is just a breadcrumb for us to recover our path back to the start. Yeah, so that makes sense, I think. Alright, I'm going to put this nice little dotted line down here, kind of delineate where I'm at. Take a drink, and let's continue. Now, size 3. There's only one set of size 3, because this follows all combinations, which is the same as binomial coefficients. So yeah, it's the middle value is going to have the most. In this case, 2. So for size 3, we just have the one set, B, C, and D. Now we have to iterate over each endpoint, right? So given this history, we could end up in any of those spots. So this will be slightly more interesting here. So we'll have B, C, D, ending up in B, because now we have a choice. I'm going to say it's going to be the min of, well, we have 2 options here. We can go, so if I take B out of this set, I have just CD, right? So I can come from CD, but I could come from C, I'll put this OR here, or it could have come from D, right? So this is now this is where the recursive rule really kicks in. I was technically doing that over here, but there is only one thing to minimize over. Now I have a choice of 2 different x's, if you will. I'm just going to write it out like this. Hopefully it's clear what I'm doing. So again, from C to B plus the edge weight from D to B. I'll just put this little arrow here. So the first one, let me come look this up. It's over here, right? Which is going to be 14. So going one step into the past, we know the cheapest way to end up in C, given this history, is 14. Really, it's the only way, but plus going from C to B, which is going to be a cost of 6, or this other one. So if I drop down 1, C to D, ending in D, that's 27, plus D to B is 4. So this is clearly cheaper, so it's going to be 20. I'm going to do the parent map right away, since this is now non-trivial. So the parent map for this is going to be where we came from, is this first one, right? So this is the entry corresponding to C. So remember that C is the endpoint that minimizes this. So that's one we need to remember. This is why this algorithm is cheaper than n factorial, because we're just ditching. We don't care anymore about the possibility of ending up in B having come from D. It's just not important. So now let's move on to the next. B, C, D, ending up in C. There's the min of. Again, we'll take C out of this history set. So we have a choice here of, we have B, D is our history. We could have come from B. So B to C. Or we could have come from D. so I have D to C. So arrow here. BD. So this entry is right over here, and it's 10. Ta-da. Plus, going from B to C, that's a cost of 7. Or, I can look up this other entry over here. It's just a cost of 4. Wow. Plus, D to C, that's 8. So this is 12, which is better than 17, so we'll pick that, 12. Now, in the parent map, I'm just going to remember that D is what minimized that cost. Oh, I forgot my curly brace there. Right? So now we just need to do the last possible endpoint here. So now I have C, B, C. So that means I've visited all 3 places, B, C, and D, and I'm ending up in D. So the cheapest way to do this is between these 2 choices of, again, taking D out of this set. We have just B and C. Meaning if we ended up in D, we could have come here via B. So B to D. Or we could have come here from C. Okay, so for this value here, we'll go look this up. It's 21 plus B to D is 3. Or we have this value here, so having ended up in C, given B and C, it's going to be 8, plus the cost from going from C to D is 12. So that's 20 versus 24, so 20 is going to be the answer. Right? I should underline that up there just to be consistent. And then finally, let's do the parent map entry. So what minimized this is, in fact, C. Okay, so now we can actually almost forget all this. We just need the parent map from this previous time step. But at size 3, now we know, given starting in A, having visited B, C, and D, we know the cheapest route to end up in B, to end up in C, or to end up in D, 20, 12, or 20 respectively. So now we just have one step left. I'm going to kind of slide this over. Let's say this is sort of like a, you can say it's either size equals 4, or you can think of it as a like a post-processing step, or yeah, sort of like a special step at the end. So going back to A, so I could write it out like this, where I can say, okay, let's do A, B, C, D, ending up in A. equal the minimum of okay, so this means we have a few choices, so we can end up in B, B to A, or, so having visited everything, ending up in C, plus going back from C to A. So this means, yep, we've visited B, C, and D. Now we're ending up in D and going back from D to A. So for this first value, it's over here, it's 20. So we have 20 plus edge weight going from B to A is 2. I'll put B in parentheses here. The next one down is this C entry here, so it's going to be 12 plus going from C to A is 9. Put that over here. So this is 22, this is 21, and finally this other entry here is down here. So we have 20 plus going from D to A, that's a cost of 10, 30. So that's going to be the answer. And oh, for completeness, I'll put this here. So that means C is the cheapest way. So given our full history, we want to go through everything, end up in C, and back to A. So now we're going to rewind. A is where we start and end. Here's C. So now let's look at this history. Let's look at the parent map corresponding to this entry here, right? That's over here, right by my finger here. So we look at the corresponding parent entry, it's going to be D. We take C out of this, right? So now we have BD coming, ending in B, or excuse me, D, which is over here. Oh, let me scooch this over a little bit so you can see. If we take again C out of this, we end up with just BD. And we want to end up in D. So that's the parent map entry we look up. And then B, put that down over here. And then we take D out of this, so then we have B, which goes back to A. Now, this is actually the reverse order, so we just turn it around and go A, B, D, C, A. And if we look at that over here, if we go A to B, B to D, D to C, and then C to A. So the answer is this sort of outside walk. And that's it. So for the time, it's going to be n squared 2 to the n. That's rough. But it's better than n factorial. Yeah, so that's it. Held-Karp for the Traveling Salesman. We did it. Woohoo!